Maths educational video. This is the first video on a new topic known as multiple integrals. In this video, we will learn how to find integral of a function of two variables over a special domain, a rectangle. But first, let's recall what we learned from single variable calculus course. When we have a function fx, positive, defined on an interval a to b, the area between the curve and the x-axis over this interval is given by the definite integral as shown in the box. Now in our setting, when we have a function of two variables, the graph is a surface, as we already know. Instead of area under the graph, we should not be talking about volume under the surface. The natural question to ask is, how to compute this volume? Will it be given by some form of integral? And the answer turns out to be yes. This volume can be found by computing either one of these so-called iterated integrals. Before we move on to talk about how to compute iterated integrals, let me make a remark on notations. In subsequent videos, we will extend the case when D is not necessarily a rectangle, but a more general region. So it's good to have a general notation. So in general, integrating a function fxy over a region D can be written in this form. Double integral with the region of integration indicated below. And we write dA. dA means dx dy. You can think of dA as integrating over an area. So A for area. So this is a commonly used notation that you will find in many calculus textbooks. It's time to talk about computation of iterated integrals. First, we focus on the first of the two iterated integrals we saw in the earlier slide. If you are doing this integral, what you do is you compute the inner integral first, the one with a dy. And when doing this, we have to keep in mind that y is a variable and x is a constant. So computing this integral will give us a function of x. Y will disappear because when you integrate a function with respect to y will eventually be substituted with the integration limits, but x will remain, which is why we will get a function of x. Obviously, what you now need to do is to replace this integral in the box with gx. And now you end up with an integration in one variable. So that's how we compute iterated double integral. As for the case where you have dx and dy, you do the same, computing the inner integral first. This time, you expect to get a function of y, because x will be replaced with the integration limits. And finally, you will integrate this function of y with respect to y. I'll show a numerical example later. It turns out that these two iterated integrals are the same if the function f is continuous. And most functions we encounter are continuous, so it's something we can take for granted. Interestingly, when the function f takes a special form, which is a product of two functions, one in x only and the other one in y only, then the iterated integral, whichever it is a product of two integrals, one for x and one for y. It's something pretty easy to prove. I'll leave the proof to you. It's time to look at a numerical example. We ask to find the volume of a solid bounded between the surface and a rectangular region. We know this is a rectangle because x lies between two constants, and so does y. So immediately we'll write the volume as an iterated integral. As we know, either one of these will work. One natural question to ask is, which one to use? That really depends on which one will be easier to compute. In this case, there is an advantage of one over the other because we have something like polynomials in x and y. So it doesn't really matter which one you use. There are situations where one is easier to compute than the others, and this you will see in subsequent videos. So let's focus on the first one, since it doesn't matter which one we use. Recall what we learned earlier, we will compute the inner integral with respect to y, keeping in mind that now x is a constant. So the first term, you will keep 9x squared and integrate y squared with respect to y. That will give y cubed divided by 3. Integration of the number 3 with respect to y will give 3y. And now we will substitute 2 and 0 into this function, into y, and leaving x as it is. After simplification, we will get 24x squared plus 6. And now in this function, we integrate with respect to x over the interval minus 1 to 1. And you get the volume of 28. And we are done.